In the last few videos, we have been studying the Doppler effect for sound. Generally, the Doppler effect is a change in the observed frequency of a wave due to motion of the source and or motion of the observer. At this point in the module, we've already learned about the Doppler effect in the case where the source is moving, but we have not looked at the Doppler effect in the case where the observer is moving. A note of caution here, this video will make a lot more sense to you if you have already watched the previous videos where we looked at the Doppler effect just due to the motion of the source. So if you haven't seen those videos yet, go back, watch the earlier videos, and then join this video. Anyways, as I was saying, in the previous videos, we looked at the Doppler effect for sound waves in the case where the source of the sound is moving, but not the observer. In this video, I'm going to show you a formula we can use to calculate the change in observed frequency of a sound wave, which incorporates both motion of the source and motion of the observer. Let's start with this figure here. Over here, I have a speaker. The speaker is the source of the sound, and I have shown the speaker moving with a speed v sub s. Over here, I have an observer, and I have shown the observer moving with the speed v sub o. That subscript there is o for observer. Before we can start talking about this equation down here, a crucial thing that we have to do first is go into that space between the source and observer and mark a point somewhere in that space between the source and the observer. So I've already done that. I went into the figure and drew a little star notation here. That star will be our point that lies between the source and the observer. We're going to see that how we use this formula depends on whether the source is moving towards that point or away from it. And it's also going to depend on whether the observer is moving towards that point or away from it. So let's go over the formula now. The symbols which appear in the formula include f sub o, that is the observed frequency. The observed frequency is the number of compressions per time received by the observer. We have f sub s. F sub s is the source frequency. The source frequency is the number of compressions per time produced by the source. Then we have lowercase c represents the sound speed. And then we have VO and VS, which are the speeds of the observer and the source. Anyway, here's how we use the equation. Notice that in the numerator, I have the observer speed divided by the sound speed. And in front of that, I have a plus or minus notation. The idea here is that when we use the formula, we pick either the plus sign or the minus sign based on the motion of the observer. If the observer is moving towards that marked point, we pick the upper sign, the plus sign. If the observer is moving away from that marked point, we pick the lower sign, namely the minus sign. Now let's go to the denominator. In the denominator, I have 1 minus or plus the source speed divided by the speed of sound. In the denominator, we have to pick either the minus or the plus based on the motion of the source. If the source is moving towards that marked point, then we pick the upper sign, which is a minus. If the source is moving away from that marked point, then pick the lower sign, which is a plus. So a quick summary of this. The sign you pick in the numerator is based on the motion of the observer. The sign you pick in the denominator is based on the motion of the source. If the thing in question is moving towards that marked point, then you pick the upper sign, which would be plus in the numerator or minus in the denominator. If that object in question is moving away from the marked point, then you pick the lower sign, which would be the minus sign in the numerator or the plus sign in the denominator. We're going to do a simple example problem to practice using the formula. So here I have a bat, which is chasing an insect. The bat is moving through the air rightward at 8 meters per second. The insect is moving through the air rightward at 3 meters per second. So the bat's going to try and use echolocation to figure out where the insect is. So the bat emits a sound with a frequency of 50,000 compressions per second. We want to know what frequency does the insect hear. Now, as an aside, this is not really my field, but you might be wondering whether the insect actually hears a sound produced by the bat. So a while back, I put this question to my sister, who is an entomologist, and she looked into it. And apparently there is some evidence that insects actually hear the sounds produced by bats that are trying to eat them. So anyways, it seems that the insect actually may very well hear that sound produced by the bat, but as we're going to see here, at a frequency which is different than what was produced by the bat. So let's just start by taking this formula and copying it over. Okay, first step here, before we use the formula, is we have to mark a point which is somewhere between the bat and the insect. So how about that point right there? Now the observer here is the insect. The insect is moving away from that point. So looking over here, if the observer is moving away from that point, then we pick that minus sign in the numerator. The sign in the denominator is determined by the source motion. The bat is the source, and the bat is moving towards that point in the middle. So coming over here, if the source is moving towards that point in the middle, we pick the upper sign, which would be that minus sign. So all we have to do now is make our substitutions. Although before we do that, I'm just going to copy the equation one more time using the selected signs. And I just realized that I forgot to tell you the speed of sound. We're going to take that to be 345 meters per second. Now let's substitute. F sub O is the observed frequency, or the frequency heard by the insect. So we're going to put in the source frequency, 50,000 compressions per second. Then 1 minus the observer speed is 3 meters per second because the insect is the observer. We put that over the sound speed, 345 meters per second. Then in the denominator, we have 1 minus the source speed. The bat is the source, and the bat speed is 8 meters per second, then all over 345 meters per second. So substituting and then rounding off to 3 significant digits, I get that the observed frequency is 50,700 compressions per second arriving at the insect. So now we have done our first example problem where we calculated the Doppler effect due to both a moving source and a moving observer. We're going to do one more example like this in the next video, but with a bit more complexity.